The 2026 FIFA World Cup spans 3 nations, dozens of time zones, and massive venues like the Estadio Ciudad de Mexico. This tournament tree illustrates the mechanical shift. Expanding the field from 32 to 48 teams injects a massive variable, the round of 32. To lift the trophy, a champion must now survive 5 consecutive single-elimination matches instead of 4. Every additional knockout game is a high-variance filter. Events like an early red card or a late-stage hamstring injury compound with each extra 90 minutes. This matrix tracks how major forecasting models process that variance. Goldman Sachs calculates a 26% probability for Spain. The academic model from the University of Innsbruck drops them to 14.5%, and leading economic models project a Netherlands victory. This specific tournament is projected to generate 2 exabytes of real-time data, powering live tactical analysis across 30 days. Yet, when identical inputs are fed into institutional algorithms, they output completely different world champions. To understand why the math diverges, we have to build the probability engine ourselves, tracing the exact path from raw data ingestion to a 100,000 bracket Monte Carlo simulation. Our probability engine starts with 8 years of historical match data. A bivariate Poisson distribution calculates the independent probability of exactly how many goals each team will score. To prevent outdated results from skewing the math, an exponential decay weight prioritizes current form. But historical macro data has a blind spot. It masks the immediate physical impact when a generation of young elite talent enters their prime. To solve this, the model pulls individual plus-minus ratings and transfer-marked market values, quantifying the exact statistical lift provided by a player like Lamine Yamal. Live roster updates integrating players like Pedri feed granular tactical intelligence directly into the team's overall rating. This functions similarly to physics-based simulators like EA Sports, which calculate outcomes by evaluating individual attributes like pace, stamina, and positioning. Raw strength is just the baseline. Step 2 requires an algorithm to determine exactly how much each of those variables actually matters. We route this data into a hybrid random forest. By generating thousands of decision trees, the algorithm automatically tests and learns the optimal weight of each input, figuring out exactly how much to trust an ELO rating versus a country's GDP, preventing the model from overfitting to noise. This weighting process explains the divergent predictions. The Innsbruck and TU Dortmund models weigh current player metrics heavily, causing their ratings for Germany and Brazil to deviate sharply from the betting markets. This matrix isolates those feature weights. Goldman Sachs relies aggressively on historical ELO ratings and geographic trends. Because their data shows the trophy almost always returns to Europe following a South American victory, their algorithm outputs a strictly all-European semifinal. Economic models take a completely different approach, prioritizing macro variables like per capita wealth and an optimal athletic output temperature of 14 degrees Celsius. Filtering the data through those specific climatic and economic weights produces a statistical outlier, a projection that the Netherlands will win the tournament. Conversely, sportsbooks incorporate expert expectations, dynamically adjusting England's probability based on the tactical history of manager Thomas Tuchel. Predicting a winner comes down to what specific data the algorithm chooses to trust. With the weighting set, the pipeline advances to the simulation engine. The model plays out the tournament 100,000 times to calculate the odds of survival. This isolates a variable called path friction. In a knockout format, a team's success relies heavily on the specific sequence of opponents in their route, rather than their raw roster quality. This creates the France paradox. Despite fielding an incredibly deep talent pool led by Kylian Mbappé, analytical models routinely suppress France's probability of winning. This bracket heat map illustrates why. France's projected route operates with high friction, forcing them into highly efficient opponents like Spain or Argentina. Spain, however, projects into a low-friction path, securing a statistically clearer highway to the semifinals. When you map elite player metrics onto an optimized bracket route, Spain emerges as the mathematical consensus across Opta, EA Sports, and Goldman Sachs. We can see this path variance clearly with the U.S. men's national team. The Opta supercomputer projects an extremely high-friction route for the U.S., facing Argentina, Portugal, and England in succession. But running those same teams through the Find Sister Site simulation generates a completely different U.S. bracket. proving just how sensitive these engines are to minor shifts in group stage tiebreakers. Forcing a champion to navigate 5 knockout matches makes path friction the ultimate filter. Raw strength does not secure a trophy in a 40-18 field. It simply purchases a fractional advantage against probability. Tracing the math backward from the gold trophy reveals the final reality of predictive modeling. This bar chart displays the absolute ceiling for certainty. Across the most sophisticated architectures, Spain's probability to win maxes out between 14 and 26%. The field occupies the remaining 80%. Even in a highly refined algorithm, the collective field mathematically defeats the favorite 4 times out of 5. These models are not crystal balls. They are pricing engines built to measure statistical noise. The compounding randomness of the expanded structure makes the 2026 tournament the most chaotic ever designed. By combining historical baselines, live player variables, machine learning weights, and path friction, we can calculate exactly who has the clearest route. But the math stops at the touchline. The game still decides who survives the path. In 2026, the structure of the tournament itself is the toughest opponent on the pitch.